Okay, so we've got this situation. We've got a roof that has, it's got several faces, but each face has the same slope. So I'm going to draw a bad picture here. Here's the foundation, and I'm just going to draw a rectangular foundation just for bad art reasons. I don't think I could draw much better than this. And here's your house sitting up here like this. But now the roof might be some more complicated shape. Let's see here. For example, it might, oops. The roof might have several pieces like this. You all have seen this kind of thing on roofs before. But the idea is that the slope here, in other words, how steep is it there and how steep is it here? Well, there's the uphills in different directions, but they have the same steepness. It's, whatever that might happen to be. And I think that's actually somewhat standardized, at least around here. Anyway, so does everybody see what the problem's asking? We're supposed to figure out the total square footage of the roof itself. So the roof has these different chunks, and there's a chunk on the back and a bit over here on the left, etc. Okay. So let's look at the hint. The hint said that note that m is the length of the gradient. Now let's pause and talk about that. What is remember the gradient vector has these neat geometric properties, and the length of the gradient tells you the slope, right? So and that's this m thing that's been given. And all right, so let's write that down. M is the length of the gradient. Specifically, it's the gradient of the function whose graph is this roof. Okay, so in other words, this roof can be written down as z equals f of x comma y. In other words, we can parameterize, we can use the graph parameterization for this function to parameterize our roof. So, so the graph parameterization is that, let's call this, x of u comma v, and it is u comma v comma f of uv parameterizes our roof. Is everybody good so far? I mean, it's sort of, it's not clear where we're going because we don't know what this function is. But whatever it is, this definitely parameterizes the roof. And we're still not sure why this is going to matter, but let's just kind of press on. So, okay, so now we have to compute xu and xv, and we have to take their cross product to get our capital N vector, and there's some calculations in here. Here you get 1, 0, fu, and then here you get 0, 1, fv, and then the cross product is, let's see here, the cross product is negative fu, negative fv, 1. And then our stretching factor, there's so many calculations in this, but the length of capital N is our stretching factor, and that ends up being the square root of 1 plus fu squared plus fv squared. We still don't know what these functions are. I claim that they're going to disappear in just a blink of an eye here. So, here it comes. What's the length of the gradient? Well, the gradient of f is just the partial of f with respect to x, partial of f with respect to y. And so this is square root of fx squared plus fy squared. Note that that looks an awful lot like this, especially since x is u and y is v. So I claim that this, what we have here, this the stretching factor, our length of n, what that is the square root of 1 plus, and that, fu squared plus fv squared, well, that's exactly the square of this, which don't forget the radical there. Namely, it's m squared. Yeah?
Can you show how you get the gradient again?
Yeah, so keep in mind that what we've got here is a function that gives you height as a function of x and y, and the definition of the gradient vector is that it's just the partials of that function with respect to the different input variables. Yeah. Yep. Does that make sense? Okay. So what's weird is we kind of proceeded on this problem a little bit blindly for a while, not knowing how is this going to work out, given that I don't know what this function is. It was, sort of seemed like we're moving around in the dark, but it just ends up that the length of the gradient, the known length of the gradient, relates directly to the stretching factor that we're using. Okay. So square root of 1 plus m squared. So here's our integral then becomes as follows. Keep in mind we're trying to compute the area, the surface area of this now parameterized surface. That surface area is, it's a double integral of, let's say double integral ds, but that's double integral of the stretching factor, length of n, du dv, and the stretching factor is that square root of 1 plus m squared. So I've got just square root of 1 plus m squared du dv. And here's the awesome news. The statement of the problem says the surface is made up of several faces, but each face has the same slope m. Therefore, m is a constant over the whole surface. M does not change, which means that this is a constant for the whole calculation, which means it'll just factor right out. And what I have then is square root of 1 plus m squared, and then just double integral du dv of just 1. And that says, this says is this the area of the foundation of the house. It's just because this is the parameter domain. That makes sense? So we have, the surface area of the roof is square root of 1 plus m squared times, times the area of the foundation. And let's see now the statement of the problem. So it says find the square footage of the roof in terms of the slope m and the square footage of the foundation. So there you go. That's it. Yes?
Why is the gradient not dependent on the z coordinate?
Because keep in mind in the setup of the problem, we're viewing the roof as being part of the graph of f. Right, so critically, f is a function that has two independent variables, and then the height is z. So that third variable z is an output variable for f, and that's just the nature of the graph construction. Right. So the function f itself has two input variables and one output variable, and the definition of gradient is that you take the partials with respect to just the input variables. So it's a three-dimensional problem. But that surface is the graph of a function of two variables. Again, this is the graph. The precise nature of what is a graph versus what's a level set, etc., is critical in this problem.
Is there any reason why we decided to choose z as f of xy
instead of
as opposed to saying like another variable p is equal to v of xyz?
The roofs are always oriented in such a way as to keep the rain out. Right, rain comes down. Down is in the z direction. So z is sort of a special coordinate when you're talking about a roof. Right. So so in particular, we know that the roofs don't ever wrap under themselves and stuff like that. So I know that I can write a roof as an equation of this sort. In other words, I know that I can view a roof as being z as a function of x and y. So I look at this function f because I know that I can do this. Does that make sense? Yeah. Okay. Anybody else? Yes.
Oh, no, another problem.
Oh, okay. So let me just say briefly before we go on to the next problem. So this problem comes from a real-world situation. Somebody asked me one time, "Hey, I've got this problem of, how do you? I need to know how much roof square footage I've got, but what stinks is A, I can't get up there. and and measure. I don't want to fall off and hurt myself. And B, there's all these different faces. I mean, you've got this face there, and that's some weird parallelogram shape, and then I've got that face as a triangle, but I can't get up and measure all of the individual lengths and measure all of the angles. It would be a very tedious problem if you don't know this observation. But the clever observation, and this following observation was made by someone who's not a mathematician, but they make the observation as that, look, every shingle you put on the roof, whether it's facing that way or whether it's facing that way or that way, doesn't matter. It's just the angle from the horizontal of the shingle that's going to correspond to how much of a shadow it's got down on the foundation. And details aside, so now the nature of this formula, this non-mathematician couldn't come up with. But the idea that, hey, if you've got a constant slope on all your faces of your roof, then there's just going to be a constant factor that relates the roof area to the foundation area. It was a non-mathematician that came up with the fact that there's going to be this relationship. And then it was just a little math, a little algebra to figure out what that factor is. So you can see the geometric intuition. I mean, imagine yourself being like a carpenter. And you could sort of visualize that. Look, every shingle up there is going to have a shadow, and there's more area because it's at an angle on the roof, but it's going to have a smaller cross-section projection down on the foundation, but there's going to be a constant relationship there. And I thought that was a really clever idea. So in other words, sometimes you don't have to have a math background necessarily to have a really good geometric intuition, which ultimately is kind of described by multivariable calculus. And I thought that was a pretty neat trick for someone who's never taken a multivariable calculus class before. So anyway, keep your eyes open for, you never know, in the real world, really neato stuff like that can definitely kind of come up, and geometric intuition can answer problems for you.